Alright, welcome to the programming lecture. The cat has been played with. He's in one of those moods where he just wants to run around really, really fast all over the place. And now I am back. Okay, so let's talk a bit more about animation. I know I keep teasing you with all these ideas, but this is just my plan for the next few lectures, honestly. We're going to do a little bit more with that bouncing ball that we talked about last time, okay? So I have opened up the code for all that stuff from last time. I've called it bouncingball.py now. And if we just remember what it's doing, if I run it, it draws the bounding circle, and then it makes a ball and starts bouncing it around, okay? Which is fun. I think I changed a lot of things about this ball. I changed its size, its fill color, but you can just have everything defaulted. And so I'll just comment out these lines. And so now it's just a white ball again. We can set the fill color to something cool. And keep it pink. Doesn't really matter, is the idea. Let's be red today. Alright, so here's our ball. And I talked a bit about last time the fact that it's animating. We're drawing frames over and over and over again really, really fast, and the fact that we're showing a bunch of pictures and that those change is the reason we see animation as a human, okay? So let's talk a bit more about why. So here in the code is where the bouncing is happening, okay? We say while true, next frame, and the next frame moves the turtle in the current bouncing direction. Okay, so we had the turtle direction that we used to bounce the turtle around. We just moved the turtle ever so slightly. Okay, in his current bounce direction, potentially bouncing off the wall if necessary. Okay, and so in your next, in your programming assignment that you're currently working on, you're modifying this code. And so this is what it's doing. It's moving the turtle ever so slightly in the current bounce direction, but potentially bouncing off the wall as well. All right, so up here, finally it hits the wall. It needs to go back down. It needs to change the direction. And so the next time the next frame gets called, it'll get moved in a very, very slight amount in the opposite direction because we swapped it. Okay? So that's the idea there, but why in the world is this while true? Why does this forever loop? It always loops. It just keeps on coming back to itself because the condition's always true. Why does this loop forever process, animate? Okay, so in theory, the program should never do anything, right? Like, it'll show frames so fast that you'll never see anything, yeah? Like, maybe it's always redrawing. And this is where I talk about the fact that, yes, that could be the case. Maybe you have the world's fastest computer, and so it's moving this ball around so rapidly that you don't see it. Like, it's jumping in between places when it draws the screen because it's moving so fast because your computer can draw these frames super quickly. Okay? So that is a possibility, but usually most of your computers take a while to draw to the screen. So when we say next frame, it takes some time to do that. And so in the time it took to draw this one, your program has waited a little bit, okay? It's waited a little bit, And so the next time it comes back to this while true loop to draw the next frame, some time will have passed. Okay, so that's what I want to say about that. So in theory, if you had the fastest computer in the world, it would look very choppy. But most computers take a while to draw things to the screen, and so there is time in between each call. And therefore we have animation. Okay, I hope that makes sense. If you wanted to be very, very explicit, there's a way to do it. So I think it's like Python pause, I think. Yeah, it's time, Python time. The time module. If you want to have more control about how often the frames are getting drawn, and therefore that means the frame rate, you can use time.sleep, I think. So you have to import time. And here's the documentation for the time module. Okay, so let's take a little bit of a look at this. You have all these time dot things, but the one we're looking for is sleep, I think. There it is. Boop. And so you just give it a number of seconds that you want to stop the program from executing. Okay? So it'll make the program wait. We can say 5 or 1.5. So if you wanted, at most, like 30 frames per second, you'd do sleep 1/30, right? So let's slow it down. I'll import time up here, and I'll say time.sleep 1/30. Forces at most 30 frames per second. But obviously, because it takes time to draw the next frame, it's going to wait a bit longer. It's going to be a bit less than 30 frames per second. Okay? But it will happen. So this is what happens when you make it wait. It's going a bit slower. You see that? Isn't that cool? So maybe you want almost 60 frames per second. That's like a good gaming speed these days, right? And sometimes it's a bit choppy, okay? Because it's going a bit less than that because of these next frame calls. So now you know what you can do to force these frame rates, okay? You can be a bit fancier as well. But now you know why this forever loop is really actually animating things, because it is waiting. It is secretly waiting, okay? So that was a long, involved process. I'm going to comment this out. We're not going to need it because we'll just use the computer speed to draw this ball. And now I want to talk about something really, really fun. Once this works, it's going to feel really good, okay? So we want to make the ball bounce with gravity. So for example, the ball starts up here, it needs to move down, and it needs to get faster as it's moving down. So it's like you drop it, and then it's slowly starting to fall really, really fast, and then it bounces, right? Boop, boop, and then it goes back up, and it bounces, just like that, okay? So the position over time of the ball would be like, starts up here, and bounces really fast. Gets a bit slower, bounces really fast, goes up fast, slows off, gets to the peak of its bounce. Okay? That's what we want to do with the ball. This is like time, this is position. So if you've taken a physics class, you know what I'm about to do. we're going to use kinematics. All right, so right now, our ball moves with constant velocity because of this line right here. We use this direction as the velocity. Five pixels per second, or something like that. 5 units per second. You can think of it as 5 units per second, or like 5 pixels per second, or something like that. It's really per frame, actually. 5 pixels per frame. So that's what we want. Let's pretend that frame is per second. Just to make things easier, it's really per frame. But that's not what real life does, okay? If you drop a ball, if you remember, it starts out slowly, but it starts speeding up on its way down. Okay? That's the idea. And then when it bounces, it should slow on its way up. Okay? When it's bounced off the ground and it's going back up now, it should start going up fast because it's just hit the ground with a lot of energy. And then suddenly that energy gets translated into potential energy, right? Instead of kinetic energy. If you remember any of these terms, if you don't worry. It's just to help you. So it also slows down on its way up. And how do you talk about how fast something is changing speed? Because that's what we need to worry about. So how fast does a ball in real life change its speed? Okay, that is the question we need to ask, and there is an answer. It moves, it's affected by gravity. The ball is accelerated by gravity. And gravity affects speed at a constant rate. It accelerates things at a constant rate. 9.8 meters per second squared. Okay, maybe you remember that. So the way you can interpret an acceleration measurement is, think of it like this. The ball is speeding up by 9.8 meters per second, every second, okay? Okay, so initially, maybe the ball's speed was 0. Then at 1 second, when the ball's over here, so here's the ball, speed 0. 1 second later, the ball's down here, speed is, 1 second, the speed must be 9.8, okay? Because every second it changes by 9.8, okay? 9.8 meters per second. That's what acceleration means. So at second 2, if it hasn't hit the ground yet, maybe the ground's down here, this is another second, that speed is 9.8 plus 9.8. You see that? 19.6, I think. I hope this makes sense because this is the key. Okay, we're going to start the ball up here with a speed of 0, and gravity is going to move it down at a constant rate. Okay? So let's write this in code. This is going to be really, really cool when it works, I promise. So right now it's moving at a constant velocity. We need to change the velocity each time. Okay? So the first thing that I do want to do is start the ball up top. All right, so let's start the ball up top with a direction downward. Okay, so no real changes, just cosmetic. It starts at the top because we want to drop the ball, remember. Okay, so every time I rerun this program, it's going to drop the ball from the top, just like that. Okay, so when the ball is dropped, now it's our chance to start changing its velocity. Okay, so let's work on this. So turtle acceleration equals, and if you think about it, like this is the y, like if this is the y coordinate of the ball, it's very high. It's like up here. It's like at, this is like a coordinate system, and the ball's right here versus right here versus right here. Acceleration's moving it downwards in the negative y direction. Okay? So really the acceleration should be negative something. Like we should say negative 9.8 or something. But this is probably going to be way too fast. But we can try it. Let's try a direction. Let's try -1. Let's make it move pretty slowly at the start. That'll make things easier on us. And let's have the acceleration be negative 9.8 pixels per frame, I guess. All right, so the direction is really the velocity. So let's change that actually. Pull the covers off. Every time we say turtle direction, I'd like to say turtle velocity instead. So instead of turtle direction, let's say turtle velocity. This is called refactoring. We're changing our code with new ideas in mind. I believe that's the only places we use it. Okay. Yeah, it seems to be working. Let's make sure it bounces still. We're good. All right, so now we need to affect our acceleration. Okay? Every time a frame happens, we need to let the acceleration affect our velocity. So if we're up here and a little bit of time has passed between each frame, our speed should be getting faster. We should be heading towards the ground a bit faster. All right, so the turtle position, this is where we set it right now. Using its velocity. We now need to set it including its acceleration. All right, so every frame, we'll say, the turtle goes a bit faster by a certain acceleration. Okay, so that means the velocity changes. Oops, sorry, set the velocity. Set the velocity first to be affected by its acceleration. All right, so the velocity is about to change. Up here, it was 0, but then it starts moving a bit faster and faster. Now it's 9.8, things like that. So each frame, we want it to move by its acceleration. So turtle velocity equals turtle velocity plus turtle acceleration. Okay, so the velocity changes each frame. Because it's influenced by its acceleration. And then finally, we set the turtle position using its velocity after updating its acceleration. Okay, so that is the idea. That's the most of it. Let's see if we get any errors when we run this now. Some weird things happen because we need to play with the constants now, but it's actually, I think it's starting to work. So let's change this acceleration to be not like Earth's acceleration. Let's change it to be a bit slower. How about 1.8 pixels per frame? Ooh, that's exciting. Okay, how about 0.8 pixels per frame? Whee! Is that not the coolest thing you have ever seen? And of course it's going to slow down a little bit. And then it's going to start going off in the distance. And so there's a slight bug in our program somewhere. And I think that has to do with how we're figuring out if it hits the wall. So it's not enough to set its velocity now. We should also put the turtle on the right side of the wall. So if he was up top, which I guess he'll never be at this point, but just in case, if the current y is, let's see here, because we're eventually going to use the current y down here, so let's just change the current y. Is greater than 200, let's set it to be 200. And then if the current y is less than negative 200, set the current y to be exactly negative 200. Okay, that's the idea, because like if it went under the wall a little, because it was moving so fast it went past the wall, we need to put it right here before we do any calculations. That's the idea. But that's legitimately all we have to worry about, I think. The ball is going to bounce, and slowly but surely it's going to lose a bit of, because of the way we're handling the, it's going to vibrate, because of the way we're handling the collisions with the wall, it's going to lose energy. That has got to be one of the coolest things I get to program in a class. Okay, so I'm really excited about this. I hope this makes sense. Okay, the only thing that's changed is the fact that we're letting an acceleration affect us. Okay, that's the only thing that's changed. We introduce some type of acceleration which is pointing in the negative direction because balls move downwards, right? Gravity pulls you downwards in the negative y direction. And then all we need to do is use acceleration because acceleration affects velocity, okay? All acceleration does is affect velocity, so we need to reset our velocity using the acceleration each time. And suddenly we have not only a ball that's moving at constant speed, but a ball that's reflecting the way that the world works, okay? So the velocity changes because the acceleration is pulling the velocity, in a sense. And suddenly we have cool things. So if you've felt bored in a physics class, just think about this now. Okay? And I think the last thing that I want to do is make sure that this is a perfectly elastic collision. It's really cool that it's bouncing like this and eventually stopping, but it'd be nice if it just keeps on bouncing as well. Okay? So we can fix that. So if ever the velocity, let's see here, I'm going to have to do a bit of physics. I'm going to have to pause the video. But if it ever hits the bottom, let's change the velocity so that it's perfectly elastic, so that the ball, when it bounces, it goes right back up to where it started. Okay, so I might have to do a bit of math given the amount of places that this needs to travel. But I think what we can maybe do is, how about we print out what the velocity is the first time, because that's pretty darn close, right? Let's try that. So the first time it bounces, let's print like where it gets to right there. The first time it hits the bottom, let's print its velocity down here. and then that'll let it bounce almost as high as it was. So how about I print turtle velocity when it hits the bottom wall, and then we'll stop the program the first time it hits it. And then I'll just reset it to that. That's a cheat. Okay, so it's about 25. Okay? Yes, I do want to kill it, except quit stops the program. Okay, so it's 25. This is just a constant. It's influenced by the initial velocity and acceleration. So if you change those, you're going to have to change this. So I think by resetting it, whenever it hits the wall, it's going to bounce perfectly elastic. Boop, boop, always going back, because we're giving it a speed and a position, and it's going to be affected by gravity some more. It's just going to keep on bouncing to that top spot, moving really fast, moving really fast. Isn't that cool? So now we have a bouncing ball. I don't know how well you're seeing this. It depends on how well this program is like getting displayed to you through YouTube, but it is moving a bit fast when it's going down there. Then it slows down. Please run this yourself. So you can comment out this line right here to have a ball that loses energy. And the way it loses energy is because of it might go a little bit past the end, and then we spin it around at that point, okay, when we notice it's past the end. So it's kind of a hack, but it works out to be extra lifelike. Okay? So either way, I think this is really cool stuff. And there's no way I can start the next thing, but I'm going to explain what I want to do next, and then we'll make it happen in the next lecture, okay? But we have just made a ball that bounces and potentially loses energy depending on whether or not we do things. And we've just modeled it using standard physics equations. Isn't that the coolest thing in the world? Okay, I'm very happy. I hope you are. Yeah, so that's this. And this is a complete program. Please yell at me in office hours or on Piazza if this is not making sense, because this is fun and I want it to make sense for you. Okay, the next thing that I want to do is program this little bouncing square. If you watched The Office, you might have remembered this episode where they're all like fascinated by this little DVD icon, and they want it to hit the corner, right? So if you haven't watched The Office before, don't worry about it, but it is fun, and we're going to program this. Okay, so we're essentially programming the bounce block, if on edge bounce block. From scratch. If on edge. Or if touching edge. One of those. Bounce. So we want to implement this block in Python. Okay? And we want it to work not just in one direction. We implemented it for one direction, like the ball's going up here, then it needs to go down here. We want to implement this in both directions. Okay? So here is the game plan there, and we'll talk about it, and I guess we'll have to implement it next time. So we want to make a square, okay, or a rectangle, whatever we want. Here's our screen. We want to make I'll use a different color. We want to make a rectangle, okay, or a square. How about we make a square? So draw the screen boundaries like we're doing. Make a square in a random location within the boundaries. And then we need to give this square a direction, okay? So it's got to be like, okay, it's bouncing that way, or okay, it's bouncing this way, or maybe it's going straight down. Who knows? It should be random, yeah? Give the square a random direction to start. Okay, so give it a little arrow. It's like, all right, you're moving this way to begin with, so please move that way. And the idea is, if I draw myself a second square, the idea is it's going to move in that direction and then bounce off the wall when it hits one. Okay, and it's going to keep its direction and bounce in the way that it normally would, and it's going to like eventually move around to different places and maybe even the corner, who knows. Okay, so it's going to bounce. So when it bounces, it needs to go that way. Okay, that's a bounce. Bounce off wall. Okay, so we need to give it a random direction to start, and it needs to move in that direction as long as possible. So forever, another forever loop, of course, because that's what animation is good for. Forever, we want to bounce off of the wall. We want to move in the current direction. Unless we hit a wall. This is very similar. Very, very similar to our bowl. It's just multiple directions now. Okay, so move in the current direction unless we hit a wall. So if we hit a wall, we need to bounce. And we need to bounce in a certain way. Okay, so now we need to talk about, this is the high-level idea. How do we go and implement this? Okay, so let's talk some more. Okay. So how are we going to represent the direction of our little square? Okay, so we know that we can use the turtle and make him a square. We can do this. Shape. Turtle.shape is, Turtle.shape is square. We can make the turtle a square. And he'll have coordinates that we can use. So we'll know that, like, okay, the middle of the turtle is therefore, like, it starts at 0, 0 or something. It's some current location, like maybe it's 42, 42. So we know the current location of the turtle based on its coordinates. We can get those just as usual. But how do we represent the fact that the turtle needs to move in a certain direction? Like the turtle needs to bounce, or not bounce, but just become animated and go over here. Okay, how do we change this turtle in that direction? So how do we store the direction? And the answer is we can again use offsets. Except we'll use using an offset. This time we'll have 2. So each frame, the idea is each frame, move the turtle in its wider, in a bit of, how do I want to say this? Move the turtle's X and the Y direction. By the direction amount. So what that means, how does a direction dictate like a coordinate offset? Here's how. So it's like each frame, please, Mr. Turtle, move like 2 pixels in the X direction, in the positive X direction, and 3 pixels in the Y direction. So plus 3 in X direction, and, oh, sorry, maybe 3, 4 then, plus 4 in Y direction. Okay, so with that, like the next frame, if we do this, just add 3 to the X, add 4 to the Y, the turtle is going to move sideways. That'll allow the turtle to move in any direction. you can represent it using these offsets. Okay, because then the turtle will end up over here. I'll draw him in blue, or maybe rainbow is a good idea still. So then the turtle will be over here because the offset was 3, 4. Yeah? Boop. So now the turtle's here. If I can make a square of the same size. And now we know his coordinate is, it's going to be 42 plus 3, and then 42 plus 4. So 45, 46. And so that will create the animation. We can represent any potential movement with an offset. Okay? There's always an XY offset to move in any direction. So the turtle can move in any direction, and that's exactly what we want. Okay? So, how will we bounce now is the main question. And if you remember how we did it, in this program, it's going to be very similar. We're going to check if it's tried to break past the wall. Okay? Okay, so we know the coordinates, we know the bounds of our turtle's playfield. It's like maybe this is negative 200, 200. Maybe this is, no, sorry, negative 200, negative 200. This is maybe 200, 200. The turtle has all this room to play with, and so we know if the turtle ever tries to go past it, like if it ever tries to go in this direction, we know when it's hit the wall, because the turtle will have passed the minimum. So the turtle hit the sidewall when, in this example, the turtle hits the sidewall when its x-coordinate is less than negative 200. Okay? Or less than or equal to negative 200. That's the idea. Okay? It's the left wall, I guess. And the right wall, it's hit when the x-coordinate is greater than or equal to 200. Okay? For right wall. So the turtle's over here, and it tried to go a bit past this wall. We know it had hit it. Okay? Technically, it's exactly equal to 200, but we don't have to be that fancy. Just be like, okay, if the x-coordinate ever gets bigger, we know we've hit the wall at some point. Maybe we're moving so fast we got all the way over here. Who knows? And then if the direction is this way, we need to like bounce off in the other one. Okay? And it's very similar for the top. Okay? We know that the turtle has hit the top when the y-coordinate is bigger than or smaller than the top or the bottom. 200 and negative 200. Okay? Okay, so that is bounds checking. That's how we keep the turtle in its bounds. And we know we want it to bounce if it hits the wall. So we know how to hit the wall now. We know what it means to check if the turtle hit the wall. Now we need to talk about what it means to bounce off the wall. Okay, and that'll be all we talk about today. So if the turtle has a direction, remember it always has a direction, and it's hit a wall. Okay, the turtle wants to go this way, but it's hit a wall and it cannot. We notice that it is bounced. Where does the turtle need to go? So it was going this way, going this way, going this way. It needs to go in this direction. Does that make sense? Okay? So this is old direction. This needs to become the new direction. Okay? And the direction is given as an offset. Remember, there's an x offset. There's a y offset. How does it need to change when it hits the sidewall? So maybe take a look and see what it means to hit the sidewall. So maybe pause the video, take a second to be like, all right, what does it mean to make this new direction here? It's got to look like this. This needs to be the new offsets. Okay, so if you've stared at this long enough, you'll have realized that, all right, the y offset didn't change for the sidewall. Keep the same one. The x offset, however, became negated. Negative x offset. Okay, you negate the x offset if you hit the sidewall. Any of the sidewalls, in fact. Because the same exact thing happens over here. So the turtle wants to move in this direction. This is its offset, and it needs this new direction now. It needs to bounce off this way. It's again negation of the x direction. It still needs to go up, but it needs to go not over this way on the x-axis, but over this way, so that when we add them together, it goes right here. Okay? So that is the beauty of this, and the same exact thing happens with, a similar thing happens with this one. We need it to offset the y direction, okay? We hit a sidewall, and then negate the y offset of the direction if you hit the top wall. Walls. And this will be hit a sidewall. Okay, so I hope that makes sense. I know this was a bit quick to explain, but we're going to implement this in great detail next week, so don't worry about it too much. Okay, so that's everything that I have for you. Yeah, we had some fun today. We have modeled real life. We have modeled physics. So hopefully that was enjoyable. All right, so that is everything that I want to talk about today. We'll get back to this bouncing square next week in the programming lecture. And yeah, I'll see you then.